This is the first exam review video for Chapter 10 for Algebra 100. And in this unit, you were working with radicals and radical expressions. So, right off the bat, let's go back to simplifying radicals. And what we remember from that is that any number under the radical sign, the radicand, cannot have a perfect square factor other than 1. So the example that's on the screen is going to coordinate with ones from your homework. So looking at this, the square root of 20 is not simplified because we can break this down. And some of you were biggest possible perfect square fans, meaning you broke this into one that was a perfect square and then the other factor, and we wanted that biggest possible perfect square. Some of you were fans of coming up with the prime factorization, of breaking down the 20 into its prime factors. So either one, if you were in the biggest possible perfect square camp, then you would have simplified that the first value there is really worth the same as 2, and that the square root of 5 has no perfect square factors, so that 5 needs to stay under the radical sign, and that would be the simplified form because the 2 has been brought out and 5 has no more perfect square factors other than 1. If you were a prime factorization person, you looked for squared values, meaning a value that was multiplied by itself, and then you would unsquare that squaring and bring it outside. So a single 2 when we unsquare, and the 5 didn't have a partner, so it stayed underneath. So then in looking at some of the ones that are on your assigned sheet, they've got plenty of them in that first set for you to simplify. Keep in mind that the number out front is just waiting for things to come out and multiply. So if we look at number 3, that 2 just has to sit there until we decide what we're going to do about breaking down the square root of 8 in order to simplify the radical first, and then all the numbers that are outside will get multiplied together. So in breaking up square root of 8, I know that 8 has a perfect square factor of 4, and that the other factor to multiply and make 8 is 2. So therefore, again, bringing that original outside 2 down, the square root of 4 is 2, and then that square root of 2. And then finally, we can multiply those 2 values together that are outside the radical sign. And so that 2 times 2 outside the radical sign becomes 4 radical 2. And because the yellow calculators can do this, I'm going to expect to see the work on here that shows that you can do it without the calculator. So if you're using a calculator that does it for you, you need to show all the in-between steps, just like everybody else. So number 5 sometimes worries people because of that 1/3, but just like number 3, that 1/3 is just sitting out there until things come out of that square root of 48 in order for us to simplify it. So in looking through square root of 48, square root of 48 breaks down as square root of 16 and square root of 3. So therefore, I'm going to get, bringing that 1/3 down still, multiplied by 4, multiplied by square root of 3. And when you multiply 4 times 1/3, you get 4/3. And that would just sit next to it as its multiplied value. You could pause the video here and finish up the last 2 in that set. The second objective, it talks about what to do when you've got multiplied radicals, and so we called them bad breakups. We said if somebody presents 2 or 3 radicals multiplied together, it really meant that they broke that up and hoping they could simplify it, and maybe that's a bad breakup. So I'm going to look at number 7, and in number 7 right away, I've got 2 choices. Okay, and these are in general your 2 choices all the time, just depends on the way you see it. Some people see this and say, well, that one really is 5, the square root of 25, and that one really is 2, and therefore this should be 10. Some people say, well, I always put those 2 back together. That was a bad breakup, the 25 and the 4, so I'm going to put them back together as square root of 100, and therefore square root of 100 is 10. So you can get the same answer either way. So for number 8 and number 9 and number 6, you want to go back to thinking about, do I actually know both square root values, and therefore I can just calculate right away, because 25 and 4 in this case are both perfect squares. Or, well, putting them back together, and then maybe I need to break them up differently. So if I look at number 9, I do not know the square root of 2. I do not know the square root of 10, meaning they aren't whole number values, and I do not know the square root of 8. So it looks like a bad breakup. So I'm going to multiply 2 by 8 by 10 and get 160 as the value underneath the radical, so that it's 1 radical, and then I can go back to that idea of breaking it down by its biggest possible perfect square factors. And right away I see that 16 is a factor of that, and 16 is a pretty big perfect square. So 160 would break down as square root of 16 times square root of 10. Square root of 16 is the known perfect square. Square root of 10 is irrational. It has no other perfect square factors other than 1, so it can stay. So again, you could pause the video here and work on some of the ones around it. And finally, we get into the ones that have fractions or division, and 2 reminders. We cannot leave a fraction underneath the square root sign, or the radicand cannot be a fraction, and we can't leave any radicals in the denominator. So with those as our ideas, we had 2 ways that sometimes this could go. If the radical is over the entire fraction, then one way we can handle it is to split the radical into 2 separate radicals. Square root of the numerator, square root of the denominator. If the denominator is a perfect square, then we're good to go. We'll go ahead and calculate both parts of the fraction, or reduce or simplify the radical if we need to. However, if it's like the second one, where the radical is not over the numerator, it's only over the denominator, we needed that process that we call rationalizing, where we multiplied some square root value that would make the denominator a perfect square. I chose square root of 2 because multiplied by another square root of 2 becomes square root of 4, so my denominator now has a perfect square radicand, and the numerator is square root of 2. The denominator I know is actually just worth 2, and it's okay to leave a radical in the numerator as long as it's simplified. So that said, you have some in 11 and the set like that around there, 10 through 13, where you've got different fraction situations and you need to be thinking about which way you could handle them. So in number 11, I see the whole fraction under the square root sign and the bottom's not a perfect square, but 11 halves is pretty simplified, so I think I'm going to take the route of square root of the top and square root of the bottom. That doesn't simplify it completely, but it breaks that fraction up a little bit. And then that denominator is not a perfect square, so I'm going to try that idea again of rationalizing it, multiplying it by the same value, numerator and denominator. That's going to allow the bottom to no longer need a radical sign. 11 and 2 as radicals, that's just a bad breakup, so I'm going to put them back together as square root of 22 in the numerator. The denominator definitely is 2, and then I would run through all the perfect squares and see if square root of 22 had any perfect square factors. In this case, it does not, so I could leave it. And finally on 13, 13's got a radical in the bottom and no radical in the top, so the 7's fine where it is. It's that radical 12 we've got to worry about. You have 2 choices with this one. Some people would simply multiply the top and the bottom by the square root of 12, which will work. But we do know there's another perfect square we could get to faster, so we could do this. And if you choose to do that, then you're going to have to break up the square root of 12 in the numerator as well. So instead, some of you noticed that there's another radical you could multiply the denominator by that would get you to a perfect square without creating another simplified one. So some people noticed that 36 is a perfect square, so we could get to square root of 36 in the denominator pretty easily. And we'd have 7 root 3, meaning that's that multiply where they just have to sit next to each other. Then we know the denominator is 6. We would simply then check to see if 7/6 could be reduced, and if it couldn't be, then we'd be done. Finish the ones in that section then.